Answers to end of booklet questions, C5 booklet. Okay, question 1. You're given an investigation carried out by a student. Results are given here. First question is, what is the dependent variable? Well, the dependent variable is the thing we measure. Okay, so if we look down here, what have we actually measured in this reaction? The only thing it can possibly be is the last one, whether there was a reaction or not. Okay, so these are just observations. Quite often we see dependent variables are put in tables as numbers, but in this case it's just simple observations. Part B, what would we see in that reaction? A colour change in the solution, the zinc may dissolve, or copper metal may be produced. You'll be able to see it, copper coloured metal being produced. Part C, you're given the results, asked to work out the order of reactivity. How would we do that? Well, the actual answer is magnesium, zinc and copper, but you'd have to refer back to the results in the table. If you look at magnesium, it reacts with 2 other solutions. Zinc only reacts with 1, copper reacts with none. So magnesium's the most reactive, then it's zinc, then it's copper. Okay, so you refer back to those. Suggest one reason why the student should not use sodium in this investigation. It's too dangerous. It has a violent reaction with water, and the water is in the solutions. Okay. F, which metal is found in the earth as the metal itself? Gold, because it doesn't react with oxygen, water or acid. Okay, so nice easy one. Balancing equations. It's 2 iron oxide reacts with 3 carbon to produce 4 iron and 3 carbon dioxide. And if you draw out or write out each of those atoms, you can see that they are balanced. The name of the element used to reduce the iron oxide is carbon. The iron is reduced because oxygen is taken away, and the carbon is oxidized because it takes the oxygen. Okay, so carbon reduces the iron. And what is meant by reduction is a loss of oxygen. When something loses oxygen, it's reduced. Question 2. You're given another experiment here and a measuring cylinder with gas in it, which is upside down. So make life easy for yourself, turn it the right way up. And if you look very carefully at each of those graduations, you can see it's on 36. They usually allow 1 centimetre cubed either way. Okay, so anything from 35 to 37. Set of results, you're asked then to plot the graph and draw 2 lines. You get a mark for you get a mark for the points being correctly plotted and your 2 lines of best fit. I've labelled the anomalous result there. It's obvious that it's anomalous because it doesn't fit the trend, so sometimes it's useful just to mark that. What are the 2 possible reasons for the anomalous result? The only 2 that fit are the bung wasn't pushed in firmly enough. So if we look back at the equipment, if the bung isn't pushed in firmly enough here, then gas is going to escape. Now if you look at the results here, the anomalous result is much lower than expected. So a gas leak sounds like a viable reason. The second one, the measuring cylinder was not completely over the delivery tube. So again here, if the measuring cylinder isn't completely over this tube here, some of the gas will escape into the air. Okay, so both of those are viable answers. Describe the pattern of the graph up to 0.4. So we're describing here up to 0.4. The volume of gas increases proportionally to the mass of lithium used. So as the mass of lithium increases, so does the volume of gas. use some of the data they've given you to prove this. So 0.1 grams gives you 22 and 0.2 gives you twice as much, 44. Okay, next question. Why does the lime water bubble? I've labelled the delivery tube here because we need to know that. The reason the lime water bubbles is because carbon dioxide from this reaction passes through the delivery tube and bubbles out here. Okay, so I've written that up the top here. Student repeated the experiment. Suggest why there are no bubbles in the lime water. Remember, when you get a question starting with suggest, you've got to try and work it out from the information they've given you. You're not necessarily taught it. Now here, the potassium carbonate just didn't decompose, it didn't react, so no carbon dioxide was produced. Question 3. Look at the figure above. How can you tell that chemical reaction is taking place? Well, light is being given off, the metal's burning, and a gas is being produced. 3 observations you can make from this picture here. Name the product from the reaction of magnesium. In the figure, it's magnesium oxide. Magnesium needed heating before it would react. Now here, the answer is it has a high activation energy, but we haven't studied this yet, so I don't want anyone getting stressed over that. Okay, we'll come to it in C8, so we've got a way to go yet. D, a sample of the product from the reaction in figure above was added to water, and they want to know what the pH of the value of the solution would be. So they tell you it turns blue, and they want you to state the pH of the solution. pH 1 is red, pH 4 is orange, 7 is green, 9 is blue. That's the weak alkali. Why are nanoparticles effective in very small quantities? This is C3 work, so it's referring back to that information. It's because they have a high surface area to volume ratio. So that's something I want you to link to nanoparticles. Every time nanoparticles comes up, it's high surface area to volume ratio. The advantage, you only need to use small amounts. The disadvantage is they can damage our cells and they can have unknown harmful effects. H, coarse particle, has a diameter of 1 times 10 to the power of minus 6, and nanoparticle has a diameter of 1.6 times 10 to the minus 9 meters. They want you to calculate how many times bigger the diameter of coarse particle is than the diameter of the nanoparticle. So we're going to take the coarse particle size, we're going to divide it by the nanoparticle size, and the result is 625. Question 4. We've got a reaction between copper carbonate, dilute acid. The flask with the reaction mixture in is sat on a balance. First question, state symbols. Well, the copper carbonate is a solid, it shows you in the diagram, and water is a liquid. Why did the balance reading decrease? And the answer is because you produce carbon dioxide gas, which is escaping. Okay. C, describe a safe method for making pure crystals of copper sulfate from copper carbonate and dilute sulfuric acid. Use information above. 6 marks for this. Okay. First step, add copper carbonate to and state a volume, 10 centimeters cubed of dilute sulfuric acid in a beaker. Remember, we've got to name the apparatus here. Keep adding and stir until there is no further reaction. That's important. We don't want any acid left over. We want all the acid to be reacted. So that's part of the safe element of the method. Use filter paper and funnel, naming our equipment again, to filter the mixture into a conical flask. Pour the filtrate into an evaporating basin. Warm to evaporate off all the water to leave crystals of copper sulfate. You can use a Bunsen burner or a water bath. Draw a little diagram and label it if you like, showing all the equipment in there as well. Okay, so we've got 5 steps and we've named the equipment in all of those. D, percentage atom economy. We're going back to C3 calculations again, C4 calculations rather. So here we need to work out the formula mass of copper sulfate and divide that by the combined formula masses of copper carbonate and sulfuric acid. They give all that information here, so you don't have to do all the number crunching. So the formula mass of copper sulfate is 159.5, and the formula mass of copper carbonate and sulfuric acid is 221.5. You divide those and multiply by 100 to give 72%. E, give one reason why it's important the percentage atom economy of a reaction is as high as possible, so the waste is minimized. Question 5. A student investigated reactions of copper carbonate, copper oxide, dilute hydrochloric acid. In both reactions, one of the products is copper chloride. They ask you now to describe a reaction of copper carbonate and dilute hydrochloric acid to make copper chloride crystals. So it's very similar to the previous question, part C. We add copper carbonate to 10 centimeters cubed of dilute hydrochloric acid until there is no further reaction. The reaction we would see is bubbling because carbon dioxide gas is being given off here. Filter the mixture, pour the filtrate into an evaporating basin and warm gently to remove all the water. In this case, I've not named all the equipment because it's not necessary. There are 4 marks for this question as opposed to 6 marks for part C, which needed more detail. B, a student wanted to make 11 grams of copper chloride. Calculate the mass of copper carbonate that was needed to make that. So we started off with 11 grams of copper chloride. We want to know the mass of copper carbonate that's going to make that. Let's have a look at how we work this out then. We convert the 11 grams of copper chloride into moles. So we do that by dividing the mass of the copper chloride by the mass of the copper carbonate. So copper is 63.5 and 2 chlorine atoms 35.5 each. Add those together is 11 over 134.5, which is 0.0818 moles. Try and use a running calculation, but 3 sig figs is usually what we would record on the answer. 1 mole of copper carbonate makes 1 mole of copper chloride. So let's look at that. Look at the equation. There are no numbers in front of these. So it means 1 mole of that produces 1 mole of that. And 1 mole of that is made by 1 mole of that. So the reacting ratio is 1 to 1. So 0.0818 moles of copper carbonate are needed to make 0.0818 moles of copper chloride. So let's do the number crunching here. 0.0818 moles multiplied by the mass of the copper carbonate. So that's 0.0818 multiplied by 123.5. So the mass of copper carbonate needed is 10.1 grams. Part C, the percentage yield of copper chloride is 79.1%. Calculate the mass of copper chloride that was produced by the student. So the mass of copper carbonate used multiplied by the percentage is 10.1 multiplied by 79.1%, which is 7.99 grams or 8 grams. D, calculate the percentage atom economy for reaction 2. So reaction 2 is here. And it's the same calculation. So it's the relative formula mass of the desired product, copper chloride, divided by the sum of the relative formula masses of all the reactants, copper oxide, hydrochloric acid. Remember, we've got 2 here. So calculate the percentage atom economy here. MR of CuCl2 is 134.5, and the combined formula masses of copper oxide and 2 moles of hydrochloric acid is 79.5, 36.5 twice. So it gives us 134.5 divided by 152.5, which is 88%. So this atom economy for equation number 2 is much better than reaction 1. So it asks you lastly to compare the atom economies of the two reactions and give a reason for the difference. There is less waste in equation 2. And actually quoting that, water is a waste product in equation 2, but equation 1 has carbon dioxide and water as waste materials. So equation 2 has less waste, equation 1 has more waste.